Dear students, in this section, let us discuss about an important quantity, namely called the substantial derivative or the total derivative, which is very much useful for both fluid mechanics as well as it is highly useful for computational fluid dynamics. It is a very basic term, and let us try to explore the difference between a variable, a property, which is going to vary with respect to time alone, and a property which is going to vary with respect to both time and space. That is the main difference which we are going to acquire through this lecture. Let us proceed now. So let us have a Cartesian coordinate system x, y and z. A fluid element is there at time t equal to t1. At initial time, the fluid occupies position say 1 and is moving with velocity say v1. After time delta t, the fluid element 1 is now at a position say 2. So now the fluid element occupies a new space and corresponding to time say t2, corresponding to time t2. Just we are now considering a fluid element moving in space from position 1 to 2 as shown in the diagram. This is very fine. This is okay. Now in order to establish this substantial derivative, first of all we should explore the concept of Taylor series. So we know that Taylor series is given by f of x plus delta x will be equal to f of x plus dou f by dou x into delta x by 1 factorial plus dou squared f by dou x squared into delta x the whole square by 2 factorial plus dou cube f by dou x cube into delta x the whole cube by 3 factorial plus the term continues up to infinite number of terms we can have for the Taylor series. So to know more about Taylor series, you may please go ahead with the earlier video session where we dealt with Euler's equation and Bernoulli's equation, Euler's equation of motion and Bernoulli's equation. There we have already given a lot of information what is the usage of Taylor series and how it can be adapted to the particular need that we have already explained in the session. So please go through the video on Euler's equation of motion and Bernoulli's equation before, if you want to have more about Taylor series. If you are already aware of Taylor series, let us proceed from here. Now, even though I have drawn the particle from 1 to 2 here, now I have moved the particle element from 1 to 2, but when the time is very, very small, delta t, there is a possibility that 2 can be very, very close to 1 itself. Even though I have drawn 2, which is far away from 1, but when delta t is very, very small, there is a possibility that 2 can be very, very close to 1. This is the idea just now I want to share with you. So delta t doesn't need to have this much of difference. In order to understand, we have drawn them separately, but fairly speaking, if delta t is going to be very, very small, then there is a possibility that this fluid element may be very, very close to 1 also, very, very close to 1 also. That is a real fact. That is a real fact. Now, when this fluid element is moving from 1 to 2, there are a lot of properties associated with the fluid element is getting transported. I will repeat the statement. When the fluid element has been moving from location 1 to 2, there are a lot of transport properties which is moving from 1 to 2, So what are they? They can be either scalar or vector. They can be either scalar quantities or vector quantities. What is by scalar quantity? I will now tell rho. Now rho is nothing but density, is a scalar quantity which is nothing but rho is a function of x comma y comma z and t. What is this x comma y comma z and t? This rho at 1 will be what? Rho of x1, y1, z1 and t1. Otherwise I will write it slowly. Now rho is a variable which is going to vary with respect to what? X, y, z, not only x, y, z but also with respect to time. That's what I am telling. Now density is a variable, is a property which is going to get varied with respect to not only x, y, z but also with respect to time. So what I can tell means, what will be rho 1? Rho 1 will be equal to rho of what are location corresponding 1. So it is x1 comma y1 comma z1 comma T1. I hope now you got it. Now you got it. Similarly, what will be row 2? Row 2 will be row of x2, y2, z2, t2. Now this is a scalar quantity. Now this is a scalar quantity. We can even write the vector quantity. Now if I have the velocity of this fluid element as capital V, which is the residual velocity, but if I can have the individual components, then it will be u, v and w. U along the x direction, small v along the y direction and w along the z direction. So now u, which is nothing but the velocity along the x direction, is a function of what? Once again, x, y, z, t. So u is also a function of what? X, y, z, t. What I am about to mean here is that whether the quantity is a vector quantity or a scalar quantity, it will vary with respect to space and time. The space coordinates are x, y and z, and the time coordinate is t. Why we are discussing about this one? Because the fluid element is moving from 1 to 2. When it is moving from 1 to 2, it transferred a number of quantities like density, your u, your small v. V will also be equal to what? We have a function of x, y, z and t. What about small w? Small w will also be a function of what? X, y, z and t. Yeah, another, if you want to tell another scalar quantity, then temperature. Capital T is for temperature, small t is for time. So capital T is also a function of what? X, y, z, t. So finally what we are about to tell is that any quantity, whether a scalar or vector, can be represented as a function of x, y, z and t, which is quite obvious. Now we will continue with the further session. When the Taylor series can be applied is that when delta x is very, very small, then we can reduce the number of terms involved in the Taylor series. How it is? Now you see, now the delta x, in this equation what is the variable? Now the delta x is the variable. Okay, when the delta x is very small, let us say delta x equal to 0.2. What will be delta x squared? Delta x squared will be still further reduced. 0.2 into 0.2 will be equal to what? 0.04. So what I am going to tell about the Taylor series here is, this quantity delta x is already small, which means delta x squared will be still smaller, then delta x cube will be still further, it will be very smaller. So which means I can neglect the higher order terms when I am going to consider delta x to be very small. When I am going to consider the delta x to be very, very small, which means I can neglect these terms. Because the value of delta x squared become very small, delta x cube will become very, very small. So we can neglect this higher order terms. So it is enough to have the first 3 terms of the Taylor series or first 2 terms of the Taylor series. On the left hand side is f of x plus delta x. Okay, that's fine. So the Taylor series, we have reduced it to only 2 terms. When this Taylor series can be reduced to 2 terms only? When delta x is very, very small only. When delta x is very big, then delta x is big, I can't neglect the higher order terms. I have to take the higher order terms. But in my case, I am going to consider the delta x to be very small. So automatically delta x square and delta x cube and higher order terms will become negligibly small, and they have been removed from the Taylor series. Okay. Now what is the usage of this Taylor series with respect to the parameters what we discussed, like row 2 and row 1. Now when delta x is going to be very small, the 2 will not be here. The 2 will not be here. The 2 will be almost very, very close to here itself. Got what I am telling? So 2 doesn't goes up to here. 2 will be only here. Why? This is at location x. This is at location what? X plus delta x. So now what is the difference between these two things? It is nothing but delta x. Now the fluid element has moved through a small distance, say delta x. In a time delta t. In a time what? Delta t. That's what I told. Here what are the diagram I drawn is for your understanding. But definitely the fluid element need not to go up to here. It's a slight movement. Like this what I shown. So now the delta x is like this. Then I can apply the Taylor series. As well as we have seen, I hope I can erase this one because already I have moved the fluid element very close to the 1. So you can see here, rho is a function of rho of x, y, z, t. Now this location what is the row is called as row 2. This location what is the row is called as what? Row 1. Now the main advantage of the Taylor series is that if you know any function at x, then you can find the value of the function at x plus delta x. I will repeat the usage of Taylor series. If you know the value of any function at x, then you will be in a position to find the value of the function at x plus delta x by using this expression. That is the main use of the Taylor series. If you know the value of the function at x, then it is possible to predict the value of the function at x plus delta x by means of this expression. Now, this f of x plus delta x is similar to your rho 2. This f of x plus delta x is similar to what? Your rho 2. So, rho 2 can be identified only if you know rho 1. Only if you know rho 1. That is f of x is known. Okay. So, this is at location rho 1. This is at location what? Rho 2. So, if you want to find rho 2, definitely I should know what? Rho 1. So, rho 2 equal to what? Rho 1 plus dou by dou x of, what is f here? Here the function is rho only. So, it is dou rho by dou x. What is delta x? Let it be delta x only. By 1 factor is nothing but what? 1 only. So, wherever f is there, I am replacing by rho. Wherever f of x is there, nothing but rho 1. Wherever f of x plus delta x is called what? Rho 2. Here, this Taylor series is varying only in x direction. But our fluid element is not only varying along the x direction, but it's also varying along the y direction. It's also varying along the z direction. It's also varying along the time direction. It's also varying along the time quantity. I can't tell us direction, time quantity. Okay, so which means it is not only going to vary with respect to x, but also with respect to y. So what I can write? Dou rho by dou y into delta y. I hope you can appreciate this one. How we have written this one for the x, similarly the corresponding changes in the y will be what? Dou rho by dou y into delta y. Now can you tell me what will be the change in the z direction? Yes? Yes, you are absolutely right. It is dou rho by dou z into delta z. But this overall still terms are there. Yes, still some more terms are there. What is the some more terms? It is not only varying with respect to x, y and z, but also with respect to time. So I have to write as what? Can you tell me what is the variable? Yeah, dou rho by, yeah, very good, dou t into delta t by 1 factorial. That's it. Why that's it? We are not taking the second order terms because we know that delta x is very small. When delta x is very small, delta y is also small. Delta x is also small. This will happen only when the delta t is very small. The main objective is what? Delta t is very, very small. So I will repeat once again. If I know the density at 1, I can find the density at 2 by means of Taylor series only when the delta x or the delta t is very, very small. So in such a case, rho 2 will be a function of rho 1. So rho 2 will be equal to rho 1 plus dou rho by dou x of delta x. This is okay for 1 dimensional, but for 3 dimensional, it will be dou rho by dou y into delta y plus dou rho by dou z into delta z plus dou rho by dou t into delta t. I hope you got it. I hope you got it. So this is nothing but what? This expression. Hereafter I hope there is no need of Taylor series or this one. We will just erase all these things. We will try to proceed further. So it will be, I am going to take this rho 1 term this side and I am going to write the first term as the last term of the first type. I will write it once again. So rho 2 minus rho 1 is equal to dou rho by dou t into delta t. That is, I have written the fourth term as the first term plus I will repeat the other 3 terms because this term is already taken to the other side. So it is dou rho by dou x into delta x plus dou rho by dou y into delta y plus dou rho by dou z into delta z. I hope everybody is, it's some simple mathematics. I have taken one term over the left hand side and I have taken the fourth term of the first term and I have written the other 3 terms. That's it. Now I am going to divide all the terms by delta t. I am going to divide all the terms by delta t. So what is delta t? Is nothing but t2 minus t1. So rho 2 minus rho 1 by delta t. This delta t is nothing but what? t2 minus t1 is equal to dou rho by dou t. Why? Because delta t divided by delta t. This will goes away. Plus dou rho by dou x into delta x by delta t. Or we can write as what? x2 minus x1 by t2 minus t1. If you want, you can write it. Plus dou rho by dou y into delta y by delta t. This is nothing but what? y2 minus y1 by t2 minus t1 plus dou rho by dou z into delta y by delta t. Delta z by delta t. z2 minus z1 by t2 minus t1. I hope everyone got the logic. In the next step, what we have done? We have just divided the every term by delta t. Every term by delta t is nothing but what? t2 minus t1. Delta x is nothing but what? x2 minus x1. Okay, now got it. So you can even erase this delta t by delta t because we become 1. Now This will become when if you want to take the limit T2 tends to T1, when you want to take T2 is going to T1 means what? Delta T is almost equal to 0. When the limit delta T tends to 0 or when the limit T2 tends to T1, this value of rho 2 minus rho 1 by T2 minus T1 can be called as d rho by dt, or in CFD book they may given as what? D rho by dt. Both are same. I will repeat once again. This left hand side is the differential value. The right hand side is the left hand side is the difference value. The right hand side is the differential value. So the difference value will be equal to the differential value when the limit tends to T2 tends to T1, or when the limit T2 tends to T1, or when the limit delta T tends to 0, rho 2 minus T1, rho 2 minus rho 1 by T2 minus T1 will be equal to what? D rho by dt or dou rho by dt. The differential form will be equivalent, I can't tell equal, will be equivalent to the difference form when the limit T2 tends to T1. That is the usage of max. That is the usage of max. So the left hand side, this term I can replace this term as what? D rho by dt when the limit T2 tends to T1. So there is no change in the first term. It is dou rho by dou t plus here when the t times T2 tends to T1, limit x2 minus x1 by what? T2 minus T1. What is delta x by delta t? Is nothing but a velocity component. It's nothing but u. That displacement by time, but along the axial direction. So it is u. So this quantity, when the limit T2 tends to T1, delta x by delta t will become u. So dou rho by dou x into u. I hope everyone got how I got the value of u. Delta x by delta t is nothing but what? U. Similarly, what is delta y by delta t? Yeah, you are right. Small v. Delta dou z by dou t or delta z by delta t is nothing but what? Your omega, that is the w, small w. So I can tell here as dou rho by dou y into v plus dou rho by dou z into small w. Why? Because this is nothing but my v, this is nothing but my w. So finally we got the answer. We are arriving at the substantial derivative or the total derivative. So we can see this, either I can write as d rho by dt or what? Dou rho by dou t. In case of CFD books, they may give us d rho by dt. In case of fluid mechanics book, it's not dou rho by dou t, it is d rho by dt. I am sorry, it is d rho by dt is equal to, either I can use small letter or capital letter, both are same, which is equal to dou rho by dou t plus u into, I am writing like this. First I am writing u because dot product is commutative, u into dou rho by dou x plus v into dou rho by dou y plus small w into dou rho by dou z. You put a box. The left hand side is called as the, either this or this, both are same, is called as what? Substantial derivative, otherwise called as total derivative. The right hand side, the first term is called as local or temporal, T-M-P-O-R-A-L, temporal derivative. And here what you have? UVW. UVW are nothing but what? The velocities. The velocity means in a case of our heat transfer, they are called as convective heat transfer. So these terms, whenever you find UVW, you can think about convective. So these terms are nothing but called as plus convective derivative. Why I put as convective derivative? Because there are the velocity components. Whenever there is a velocity component, we can put as what? Because of this U, V and W, I can term this derivative as what? Convective derivative. So these three terms are called as convective derivative. This is called as local or temporal derivative. This term is called as what? My substantial derivative or total derivative. So finally we establish a relationship between the substantial derivative, local derivative and convective derivative. The substantial or total derivative is equal to the local derivative or temporal derivative plus convective derivatives. Okay. We will explore further. So instead of d rho by dt, I can even put here as what? Dt by dt. I want to replace the scalar quantity rho with another scalar quantity, namely the temperature. Here capital T stands for temperature. Now can you explain me the terms? Yeah, it will be dou t by dou t plus u into dou t by dou x plus v into dou t by dou y plus w into dou t by dou z. I hope you got the logic. Now it need not to be always density. I taken density as a one of the property. It can be for any property. It can be any scalar or vector. Now I have taken both are scalar. What happens if I am going to take a vector quantity? Let me take small u by dt will be equal to what? Dou u by, wherever t is there, you replace with u plus u into dou u by dou x plus v into dou u by dou y plus w into dou u by dou z. Instead of u, can I put a small v? Nothing wrong. Small dv by dt is equal to dou v by dou t plus u into dou v by dou x plus v into dou v by dou y plus w into dou v by dou z. So wherever rho is there, replace with the t for temperature. Wherever rho is there, replace with u for vector u velocity. Wherever rho is there, replace with small v. Wherever the small v, you can replace with small w also. This is the your tangential velocity. So the ultimate aim is that we can express the scalar and the vector in case of what? The local component and the kinetic component. Now I hope everybody is clear with how to express the terms for the substantial, local and convective. Let us go still deeper. Let us go still deeper to examine the physics. Why you want to study this one? What is the difference? Like that we are going to study now. So I will take another 2 minutes to go in deeper and to analyze each and every term. Now you see here, I will take the example of temperature. It is not dou, it will be d, either capital D or small d. So dt by dt equal to dou t by dou t plus u into dou t by dou x plus v into dou t by dou y plus w into dou t by dou z. So let us take this expression. Now can anyone tell me what is the difference between dt by dt and dou t by dou t? What is the difference between dt by dt and dou t by dou t? Can you tell in words? Can you tell me in words? What is this one? The change of velocity, the change of temperature at a point, at a particular instant of time. I will repeat the statement. Dou t by dou t is nothing but the rate of change of, generally dou by dou t means what? Rate of, any quantity by time is called as what? Rate of change of. So the rate of change of temperature with respect to a point at a particular instant of time, that is dou t by dou t. Then what is dt by dt? Can anyone? And whenever I ask the students to differentiate what is the difference between dt by dt and dou t by dou t, they will tell dt by dt means addition of all the terms. If dou t by dou t means only one term, that everybody knows mathematically. But I want to explore the physics. So here I want to tell in words the variation of or the rate of change of temperature with respect to a point at a particular instant of time. Here it is not like that. This dt by dt, once again I want to recall the physics from which we derived this one. The fluid element is here and is trying to move to another location. So if we continue further, we can see this is also the change of temperature of the fluid element when it is going to move from 1 to 2. Here is moving this left hand side, this dt by dt is nothing but the variation of the temperature of this fluid element as it is moving from 1 to 2. As it is moving from what? 1 to 2. But in the right hand side, it is the change of temperature of a particle at a fixed point. It is not moving. So here it is not moving, where the left hand side is called as what? It is moving. The left hand side is called as what? Moving. So the left hand side corresponds to the rate of change of a property of a moving fluid element. The right hand side, this dou t by dou t is nothing but the rate of change of a property at a fixed point with respect to time. That is nothing but what? The local or the temporal derivative. The left hand side dt by dt is nothing but the change of a property when the fluid is moving. So if you got this idea, then you know the difference between dt by dt and dou t by dou t. And the other term is nothing but what? With respect to space. Why is with respect to space? Because x, y and z are there. So in one of the books, namely the computational fluid dynamics book by John D. Anderson, he has given a very wonderful example to understand how to clarify the difference between the total derivative and the temporal derivative. So a person is walking along a hill. So it's a very steep hill on a very hot summer day. A person is trying to climb the hill. So he's climbing up. It's a very steep hill as well as it is very hot. So this person is trying to reach almost the top. So this person is almost reaching the top, and he can see he's already sweated, he is very tired. So he can see a cave, C-A-V-E, a cave you know. So inside the cave it will be somewhat, you will have shadow. Also the temperature inside the cave will be lesser than the temperature outside, because outside it's a hot sunny day. And inside you can feel a temperature lesser than the outside temperature. So when he tries to enter into this cave, when this person is trying to enter into the cave, at the same time his friend is throwing a ice cube at him. So now he feels a temperature drop in his body because of two components. The first component is because of his friend, he is throwing a ice cube at him. He feel a temporal or a momentary or a local what? The temperature change. That is similar to your dou t by dou t. It's a temporal one at a fixed point. But as he moves inside the cave, he feels a temperature drop because of the space, x, y and z. So now if you can consider a person is trying to move from one location to another location, and when he's just trying to enter into the cave, he definitely feels a temperature drop inside the cave also. But when his friend is going to throw a ice cube at him, for a momentary time, he feels a drop in temperature. That is similar to your local derivative or temporal derivative. And once he moves inside the cave, he feels much more temperature drop because of the spatial component, namely this component. So now I hope you can understand that the substantial or the total derivative will be the summation of the local or the temporal derivative plus the convective derivative. In some other books, not some other books, many books, we can make this term as a more generic form of a vector form. What is this? Nothing but delta operator. Everybody should know what is meant by delta operator. Is equivalent to I into dou by dou x plus j into dou by dou y plus k into dou by dou z. So this operator is called as del operator. Is equivalent to I into dou by dou x plus j into dou by dou y plus k into dou by dou z. This is also called another term called as velocity. This velocity is the resultant velocity of u, v and w. So this is equivalent to I into u plus j into v plus k into w. So I is nothing but the unit vector along the x direction, j is the unit vector along the y direction, k is the unit vector along the z direction. So I hope you should know the meaning of del and v. Okay, now what I am going to do means I am going to multiply del dot v or v dot del. Both are same. Why both are same means del dot v or v dot del both are same because they are commutative, because dot product is commutative, What is meant by commutative? Either you can write x into y or y into x. Both are same. But del cross v is not equivalent to what? V cross del, which means the cross product is not commutative. You may already study in your school standard, school mathematics in plus 1 and plus 2. So this cross product is not commutative, whereas this dot product is commutative. So because of that, what I am going to do means I can either find del dot v or v dot del. Okay, let us now find v dot del. So when I am going to find v dot del means it's nothing but what? V dot del. What is that? I have to multiply I with I. So it is u into dou by dou x. J with j plus v into what? Dou by dou y plus k into k terms I have to multiply. So it will become what? Ijk. Yeah. It is w into what? Dou by dou z. So what I am telling means instead of writing as u into dou by dou x plus v into dou by dou y plus w into dou by dou z, I can treat it simply as what? V dot del. I can simply write as what? V dot del. So what I am going to write here is that instead of this big term, I can write like this also. dt by dt is equal to dou t by dou t plus capital V. Why capital V? This U, V, W can be written as what? Capital V. What is dou by dou x by dou by dou y plus dou by dou z? Is nothing but del of what? Of any variable. What is the variable here? Is temperature. Is nothing but what? Temperature. Now I hope the same one I have written in form of vector form, vectorial notation. The same thing I have written in form of vectorial notation. For example, if I want to write d rho by dt, so d rho by dt will be equal to dou rho by dou t plus v dot del of rho. What is du by dt? That also we can write. It is nothing but dou u by dou t plus v dot del of u. So I hope now you are in a position either to write in the full form or you are in a position to write in the vectorial form. I hope you can now understand the difference between dt by dt and dou t by dou t. dt by dt is because of the change of a property of a moving fluid element with respect to space and time. Whereas dou t by dou t is nothing but change of a particular property with respect to a fixed point at any instant of time t. At any instant of time t. I hope you are able to appreciate the usage of the substantial derivative, the derivation of the substantial derivative, and we will find the usage of the substantial derivative in the upcoming sessions. Thank you.